Hello, everyone, and welcome to Office Hours Live with the Meter Environment team. Today's session will focus on soil hydraulic properties, and we're shooting for about an hour of live Q&A with our experts, Dr. Colin Campbell and Leo Rivera, whom I'll introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this session to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll try to get to all of your questions. And if we don't, which more than likely we won't, someone from our science and support team will get back to you with an answer via the email that you registered with. Second, if you want us to go back or repeat something you missed, don't worry. We will be emailing you a recording of the session within the next 3 to 5 business days or so. All right, with all of that out of the way, let's get started. Today, our panelists are meter research scientists Colin Campbell and Leo Rivera. Dr. Campbell has been a research scientist at Meter for over 20 years following his PhD at Texas A&M University in soil physics. He is currently serving as Vice President of Meter Environment, and he's also adjunct faculty with the Department of Crop and Soil Sciences at Washington State University, where he co-teaches environmental biophysics, a class he took over from his father, Galen, nearly 20 years ago. Dr. Campbell's early research focused on field-scale measurements of CO2 and water vapor flux, but has shifted toward moisture and heat flow instrumentation for the soil-plant atmosphere continuum. Leo Rivera operates as a research scientist and director of client success at Meter Group. He earned his undergraduate degree in agricultural systems management at Texas A&M University, where he also got his master's degree in soil science. There he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Leo has over 10 years of experience helping researchers measure the soil-plant atmosphere continuum. So thanks for joining us, you guys.
Yeah.
Yep. All right. Okay, let's get started taking questions. Thank you to everybody who sent in questions already. And remember, you can submit your questions in the questions pane at any time during the event. All right, so let's get these pulled up here. This first question here is one that we've gotten quite a bit, and so we figured we'd open with this one, but basically it's on the topic of soil health. And the basic gist of the question is that there's a lot of interest in the topic of soil health recently. So how do soil health and infiltration tie together?
Yeah, that's a really good question. So the Soil Health Institute has identified infiltration and hydraulic conductivity as one of those tier 1 measurement parameters to indicate whether or not we're trending in the right direction. Now, it is something you have to be careful with when you make these measurements, because there are many factors that impact infiltration and hydraulic conductivity. It's not just the healthiness of the soil. Are we increasing the microbes? Are we increasing all of those things that help bind the soil together, improve structure? So that's where infiltration and soil health tie in, is if we look at the same soil type under different conditions, we can then look at impacts that soil health practices are having on this value, because in theory, if we're improving our soil health, we're improving those things that improve soil structure, and we're generating more macropores through more activity of worms and things like that. And fungus is going to help generate those glues that bind the soil together. So it's going to make a more stable soil that helps improve infiltration, which is a great thing because we'd much rather infiltrate water than run it off. So that's kind of where it ties together, along with many of the other measurements that go into soil health.
When I think of that, I mean, I think of kind of extreme cases, right? So as probably many people who are listening know, we've done a lot of work over in Fukushima Prefecture in Japan, trying to rehabilitate the soils and the environment from that nuclear disaster. And they actually went out and put down a material. They scraped off the top 10 centimeters of the native soil and put down a crushed granite material that actually took out of a mountain, crushed it, and put it down. And there we went out and looked at infiltration, right? I remember when we went out and did this, I emailed you and said, hey, Leo, can you just check our numbers? Yeah. Here's our numbers for infiltration. And you wrote back, I think, hey, those are akin to kind of concrete.
Yeah.
So when I think of soil health, I mean, maybe if we're teasing out some of these really refinements, maybe in some soil, we can't say, oh, you've got a number here and it's either good or bad. That's
Yeah.
kind of what you're saying.
Yeah.
Is we can't just say that's good or that bad unless we've got crushed granite that's applied with a roller.
Yeah.
And I sent you pictures of that, and there were literally street rollers, right, rolling back and forth on that. That didn't help.
No.
So there's a challenge there that we that the soil health, you know, there's a bare minimum. Can't roll the soil. Compaction is an issue. All of these things, and then we can kind of work up from there. That's what I hear you saying. Like,
Yeah.
hey, we need to, you know, microbes need to be active. We've got these funguses that will create these PEDs, right? And once we have PED formation, actually have this macropore, we get better infiltration. So there's a lot of information that would correlate these two things. It wouldn't necessarily cause it for sure, but there's some really good indications, and we can start by saying, you know, a good soil has a lot of these properties.
Exactly. Yeah. Yeah. So it all ties together, but you really, you need that background information. But it is one of those things that if you monitor over time, you can see the improvements and see what's happening.
So when you were, I mean, one of the things I'd like to do is hear some of the stuff you did in Texas for your master's degree, because it was a really interesting project. Were you able to identify or either, you know, I mean, either anecdotally or through experiment, some of these things?
Yeah. So that's actually, it's funny because a lot of the work I did when I was studying it was before soil health was really a thing that we were talking about.
I mean, it was a thing for us.
It was a thing for us, but we were looking at differences in land use and how that impacted soil hydraulic properties. And we had the luxury of working in these sites that had been in the same land use for 50 plus years, and maintain that way for a reason, because it's a ARS research facility. And when you went from a conventional tillage to an improved pasture to a native prairie, you saw big changes. And especially when you went from the improved pasture to the native prairie site, you saw that impact that all those native grasses had, the fact that the soil's not getting compacted by heavy animal traffic, and the grasses were healthier, the organic carbon was higher in the soil. And because of that, there was better soil structure, and there was better infiltration, higher hydraulic conductivity in that land use versus.
Was that super consistent? I mean, were you able to observe that? Just, I mean, I know you drug out these monster containers of water, because that's how you had to run this double ring. Could you see that, like, right off the bat?
Absolutely, yeah. Especially the one indicator was how many times I had to refill my trailer.
so on these native prairie lands, you literally were refilling your trailer much more regularly.
Yeah, we usually would go through 1,000 gallons of water on a native prairie site when out doing a full day of measurements, and on like the improved pasture, we could get through with half that. And so we usually only had to fill up once during the day. So just anecdotal stuff like that. But then when you actually look at the data, you can see
it was
the differences. So,
well, I mean, it's important to know that there are both of these things at play, right? That I mean, from your answer initially, I'm like, oh, we can't really go, you know, it's going to, you know, if we made a change in our management practices to system, we may never know, you know, whether that affected. And I think you gave a great scientific answer, but the other side is, you know, from a practical side, you actually can see that, right? That they're, like, all things being equal, you went out there and you could see it right away.
Yeah. So it was a really fun place to get to do research.
Yeah. Except for the weather.
Except for the weather.
I'm glad I live here.
Yeah, exactly.
Okay. Shall we try another one?
Yeah.
Okay.
All right. Okay. This next one is a pretty big compound question. So we're going to cut it into 3 segments here. They're asking about the relationship between hydraulic conductivity and filtration, irrigation decision-making, plant-soil interactions, all that kind of stuff. So the first part is they're asking basically, what is the difference between soil hydraulic conductivity and soil infiltration?
Yeah,
that's a great question.
That is a great question, and surprisingly one that we deal with all the time and see oftentimes confusion between the two. Hydraulic conductivity is, if we were to take an infiltration measurement, which an infiltration measurement is just, let's go out, let's apply some water to the soil and see how fast that water moves into the soil. But there are so many factors that actually affect how fast that water infiltrates. It's not just the capability of the soil, but it's how much is your ponding head height? How big is your area? How deep did you insert the rings? Infiltration doesn't really take any of that into account. It's just an infiltration value. So it's just how much water you're actually applying to it is actually being absorbed by the soil at that time.
So if I were teaching my class about this, I would say that this infiltration relates to the flux idea. It's how much water goes from point A to point B, just really simply.
Exactly.
That right?
That's exactly right. Yeah, that's a good way to compare it. And then when you switch over to hydraulic conductivity is that factor in the soil that is actually controlling its max rate. So when we think of saturated hydraulic conductivity, we're taking a segment of soil and we're saying, given all of the other factors being negated, no pressure head, this is the limiting factor that controls how fast the water can move through the soil given these conditions. And then that's what we would take and apply into our models that then take into account all of those other factors. So it's trying to think of something else it's akin to.
Well, I've been thinking about this because, when we teach people about movement of mass or energy in the soil plant atmosphere continuum, and I noticed both of us are studying that, Leo. So that was in our bios. So
it was.
So we better talk about this. So when we talk about this, we put up a simple equation that says flux is equal to the ability to move, the conductivity times the concentration difference. And I think this goes back to your original point that the hydraulic conductivity just talks about something's ability to move. It has its ability to move whatever we're interested in, mass or an energy, from point A to point B. Mm-hmm. And then to get to the flux, we have to multiply it by this other thing called the concentration difference. Yeah. Is there a difference between point A and point B? And you talked about like a pressure head, that kind of thing. In fact, we were talking just yesterday about the antecedent moisture in the soil that determines whether we'll get from point A to point B, right? And so if it's really wet there versus if it's really dry, that'll affect this flux, this infiltration, the F value, but it doesn't affect its ability to move. The ability to move is a kind of a native permanent thing associated with that soil, assuming other conditions don't change. We talked about roots, talked about other things. Assuming that doesn't change, that would be something static. This infiltration could be different. And you pointed out some things. And I'm thinking about just, hey, if it's a wet soil or dry soil.
Yep, exactly. If it's a wet soil or dry soil, and what are our major potential gradients? Like how much can we actually pull water throughout? There's a lot of limiting factors that can affect that. So
I got a little question as we're doing this. Mm-hmm. So I'm over there in Itate measuring this with the Saturo. And I'm sending you back emails. Hey, here's the number, and you're like, oh, that's terrible. Should I have been worried with the Saturo about antecedent water in the soil?
No, you shouldn't, because at the end of the day, what we're doing with the Saturo is we're pushing it to saturation and then using those final values to get the saturated hydraulic conductivity. Now, having said that, there is literature that talks about the impact that antecedent soil moisture can have on that final value, and it does have an impact, but it's more so in expansive soils and other areas, not as much in compacted soils.
In crushed granite put in place to that will never grow plants again. No, it probably will. With a lot of nutrients. But I think that's important to say. I wanted to go through there because initially when I was making these measurements, that's exactly what I assumed. Mm-hmm. But when maybe listening to us, other people are like, oh, does that mean I can't go out and make these measurements with something like Meter Group's Saturo? What about a mini disc infiltrometer?
That is so the mini disc is a completely different beast. It's a totally different measurement. So
why? Because
it's applying a suction and resisting the water movement out of it. So it's a tension infiltrometer, and people often try to use it to measure saturated hydraulic conductivity, but you can't, because to measure saturated hydraulic conductivity, you have to have free water, and you can't do that with the mini disc. There's a centered stainless steel plate that you put in contact with the soil, and there's a Marriott bubbler that controls that suction that's being applied by the infiltrometer. And there's no real way to go to zero suction and measure that saturated hydraulic conductivity. It's a different measurement, but it's a great tool for doing this other measurement.
It's not a bad thing that it's a different measurement.
Yeah.
I mean, I'm just making sure as we talk about it, we know that mini disc infiltrometer is not just the simple version of the saturator.
It's not. It's a completely different thing. Okay. Yeah, it's a great tool, and a lot of people love using it. But yeah, you're looking at totally different measurements.
So that actually leads us into our second question there.
Yeah. Brad, you want to?
Yeah, sure. All right. Yeah. So the second part of this question is then, if we do understand hydraulic conductivity, how can we use field measurements of water content to improve irrigation decisions?
Yeah. So I think there's a couple things that we can think about. One, if we understand what's happening in the soil, especially if we know the hydraulic conductivity, we can make better decisions about when and how fast to apply our irrigation rates, especially in understanding how deep that's going to move through the soil profile, especially if we need, depending on how deep our crops are rooting, and all of those things. And it's something that we need to understand, especially as water becomes a more limited resource. We need to understand this.
So I've got some practical questions for you, Leo, about some of the work we're doing right now. So some people here listening may be familiar with our turf grass efforts. We've been irrigating a lot of different turf grass, trying to do just what you say.
Yeah.
There's a significant amount of overuse in water and turf grass.
Yep.
And I can't remember the number, but it's our most irrigated crop here in the U.S.
Yeah.
So even though we're not eating it, my dog eats it sometimes. but I don't think that's a good thing either.
No.
So as we think about irrigating turf grass, I'm running into some interesting challenges, and I wonder if we can talk about that in context with this question, which is a lot of our turf grass that we really focus on from a dollar point of view is our golf courses, our sports fields, and things like that.
Yep.
A lot of those have sand base. They have a standard, a golf standard, for example, that they adhere to. Now, my lawn, probably like your lawn, is grown on a silt loam soil, much finer texture. What does that do with respect to this question? Hydraulic conductivity. How can we use these measurements? If I took a saturo out and measured on a golf green, and then went and measured on your new lawn that's grown in silt loam, what would we learn about it? I mean, I have my theories, but I'm curious what you say.
Well, I when I think about some of this stuff, obviously with most of these, we're irrigating from the surface and with sprinklers. And there's a whole other area of drip irrigation, which is a completely different.
We'll probably have to put that on the shelf for this question.
But what that really means is, for example, when I irrigate my yard, I actually do it in shorter intervals more frequently, because I do it at night, because I don't want water to run off my yard. Because I know that the infiltration and the hydraulic conductivity in my yard is slower. And so I want to slow that down. But also when I think about turf, it has different factors, because if you over irrigate too fast, that water can actually drain through the soil and be wasted. And so I think just understanding how the water is going to move through the soil, especially in a lot of fields that have those drainage layers, the way it retains water is completely different than the way my yard retains water that has a nice long soil profile that has in contact. So there's a lot of factors to consider there, but usually my goal is to put enough water to cover the root zone and not push it past the root zone.
Okay. So if the infiltration was slower, you brought up a good point that how can we understand these field measurements of water content? If we've got a silt loam, there's a potential that we could get runoff.
Yep.
Now I was actually thinking about it the other way.
Yeah.
So I was thinking about little short bursts for the sand to try to just keep that water in the root zone. It's only 6 centimeters, 10 centimeters deep. I was thinking about my lawn, and I was like, if I wanted to approach this to try to keep water in the root zone, maybe what I would do based on it, presumably soil infiltration, that would tell us, like with a saturo measurement or something like that that I would actually delay, maybe irrigate every second day, but a little bit longer. What would that do to the soil?
Yeah, well, I mean, that's the beautiful thing about silt loam is it retains so much more water in that plant available range. And so we can get away with that and actually help push those roots a little bit deeper by getting a little bit deeper irrigation. Whereas the sandy soils, it comes back to more so understanding the hydraulic, not just the hydraulic conductivity, but also the moisture characteristic curve of that material, knowing that with sandy substrates, we go very quickly from being in a very happy range for the grass to being in a very unhappy range for the grass.
And we live on a nice edge for sure. That's one of the things that we're experiencing as we do these, especially with the sports fields.
Yeah,
they'll dry out in a heartbeat.
Yeah.
We'll probably have 2 days on that grass. Or that sand, and then we'll dry out.
Yeah. So it's just understanding how these factors so we can keep water in the right area. And this is where, if you have sensors too in the profile, you can help understand that and monitor to make sure you're not pushing past the root zone and wasting that water, which not only is wasting water, but it's also wasting nutrients, which can be problematic in many reasons, or in many ways.
Yeah. And so we're actually doing a lot of that related to this question, measurements of water content, irrigation decisions. We do measure water content, especially below the profile, to make sure we're not washing water through. But honestly, in the profile, we're mostly using water potential to make sure that there's water available to these plants, especially when that falls off so quickly. So.
Yeah.
Okay, Brad, we're having too much fun over here.
No, that's great. I think you talked about different factors that affect infiltration rate and other things like that, and some of those factors will be also diurnal nocturnal cycles. And so this last part of this question gets into that. So how do plant and soil interactions differ day versus night?
Yeah, I might actually defer to Colin for this one because he's more the plant person than I am.
I get the plant questions.
Yeah, you get the plant questions.
Glad we threw a few of those in, so I actually get to answer something. The biggest thing that I think about day and night in terms of plants is the transpirational stream. So during the day, we have a heavy demand on the plant to remove water out of the leaves. They're gaining CO2. They open their stomates to gain that CO2, and by default, they lose water vapor. And so we can just assume that there's a large pull on the water during the day. At night, everything, if you thought about this as an elastic, so water has adhesive and cohesive properties. And during the day, this cohesive is pulling the water through the plant. We get this along a water potential gradient from the soil. It's the highest water potential to the air, which is at an extreme end of the low energy, the low water potential. And that pulls on that water column constantly through the day. And there's a gradient, a strong gradient that's pulling water out of the soil into the roots, xylem, et cetera. Now there's research going on this all the time. And we understand some of these things a little bit differently than this classic analysis that I'm giving. So understand there are caveats to everything I'm saying here. But during the night, all of this relaxes. There's no reason for plants to open their stomates generally, although, of course, this is not always true, but generally they've closed their stomates. There's the conductance. We talked about hydraulic conductivity in soil. The leaves have a conductance to water vapor, too, and that essentially goes down by a couple of orders of magnitude, at least one, maybe two. And so essentially we have no pull on that water during the night, and that should all come to kind of an equilibrium. So during the night, the plant soil reactions, it's all kind of sitting all quiet in terms of what's going on until we have the sun come up, we have a need for CO2 for photosynthesis, and then we start this cycle again. And maybe there's more to this question in terms of the interaction, but that's what I think about. That's the main diurnal driver.
Well, one of my favorite things or sets of data to look at is riparian zone data, where you're monitoring the water level in contact with the streams in these areas that are heavily transpiring during the day, and then at night everything relaxes, and you look at the water table levels, and you can see that relaxation in the water table as that demand and that pool relaxes. And it's so cool to see kind of that offset in it. It's just slightly offset with when the sun starts to come down and the plants start, closing shop for the night, and just, there's not as high of an evaporative demand, and just monitoring that. And not only do you see that in the water table data, but you can see that in water potential data throughout the profile, and it's really a cool data set to see. And I think as we get better and better instrumentation to be able to monitor this stuff, you're going to see even more interesting patterns in some of that stuff. And I think that will help us better understand some of these, especially as we're looking at some of these plants that might be transpiring at night, and helping us better understand some of those interactions.
I'm glad you pointed. I was just actually thinking about this, because when I started into this science, let's say back in the late 1990s, we could not see that during the day, and it's almost this diurnal experience. In fact, I remember going to a meeting talking about, hey, does water move in soil? Do we get this hydraulic lift? And there was some conversation about plants preferentially pulling water from lower regions, these trees, and kindly giving it up to the upper regions in the soil through their roots, and then these annual plants could gather that water, and they could go through some kind of symbiotic relationship. And I remember just sitting in these discussions and having kind of like people really get animated, like, no, that's not happening, or yes, I can prove that's happening. The good thing about today is we actually have measurements, over the years that we can show exactly what's happening. And I don't think there's any altruistic, trees, out there like, hey, how about I hand back water to these poor little plants under my branches, right? Kind of a kid story.
Yeah.
But I do think, we've observed, for example, in wheat and other things now, with the quality of measurements we have with water potential or water content, this beautiful dry down, shall we say, during the night. You can see a very clear drop, and then a flat during the day, and then a tabletop. And in some cases, especially where we have active roots in this zone, we also do see this downward during the day, and then we actually do see somewhat of a rise at night in terms of water content. So what is that? Well, we've got a relaxation of that transpiration stream, and then the water could, if there's a water potential gradient, leak back out into the soil. And so no one's kindly sharing with their neighbors, but if the gradient goes the other way, they are going to, water is going to go out, or water is going to equalize in the system. And we have instruments today which we never had. It's 25 years ago. I don't like to, even imagine. Somehow I got old. And now we do see that. Okay. I'll get off that question, since I'll talk about plants all day. So, Brad.
Well, I was going to say this is another question that kind of follows along, talking about different factors. And this individual is asking, how do seasonal changes affect soil infiltration?
Yeah, so that's another really good question. And there are absolutely seasonal impacts on not just infiltration, but the hydraulic properties of soil. And there are quite a few things, but the main ones that I think about, antecedent soil moisture, we know makes an impact, especially in soils that shrink and swell, because those soils will open large cracks. And then as you hit the wetter season, those cracks will start to close up. And so your hydraulic conductivity can change significantly due to that. But there are other factors along with the plants that are growing over time. You have active root channels coming in. And then as those root channels start to decay, you get more open pores. So there's a lot of those factors. And then also just worm activity that increases can increase and decrease seasonally. So there's a lot of those things that can change it, the hydraulic conductivity of the soil. So we often recommend, if you're trying to compare a site, and you're wanting to look across that whole site, trying to get those measurements all within the same season. Because if you do a measurement on one site, maybe in the fall, and then we go back and do it in the spring, when things are starting to change, you might not only be measuring the site differences, but you're going to be measuring some of those seasonal differences as well. So it's something that we have to take into account and understand. And soil temperature too. Soil temperature as the temperature increases, the viscosity of the water changes. And so that's another factor that can impact that. Now, there's ways to correct for that if you monitor the water temperature and the soil temperature. But that is another thing that can impact it.
So when you were out on your giant truck and it was really, really hot.
Yeah. I was monitoring water temperature and soil temperature.
Okay. So you did
for
that.
every measurement. Yeah.
Okay.
Yeah.
I've got an example of this actually, because when we were doing some of this turfgrass research I've been talking about, what I really wanted to show is a moisture release curve in situ. Yeah. So we use HYPROPs in the lab and we love those things. But I was thinking, if we could get some lab stuff done and also make a combined potential water content measurement in the field, we could do some of these things. So I actually had one of my technicians go out to the field and sample out there and run some of these in the lab. And I was really excited that these things started to match up. We had a kind of a finer texture soil out there. They called it a loam. It wasn't a loam. It was more like a sandy loam or even a loamy sand.
Yeah.
But they ran it, and those things actually matched up pretty well. Yeah. But then we ran this golf, this turf sand, this green sand, and I looked at it, and it was way off. And I'm like, hey, to this technician, what's going on? What did you do here? And it finally came out that on one, he had sampled it and then gone and kind of wet it up in the HYPROP and run it pretty much quickly from the field in there, hadn't let it dry out. And the one that I was having problems, he'd let it dry out. All the roots had shriveled, sat on the bench for a few weeks, and then he'd run it, and the thing, and the roots had changed. Yeah. And the moisture release curve was way different.
Yeah.
So it's something to think about as you're sampling. Those roots will impact, maybe not so much if you're using a clay, but if you're in a sand, you have to think about that and all the other pieces.
And that makes me think of another thing that I think people often forget is sample storage. When you bring samples back to the lab.
Wait. Undergraduate student workers don't always do what you say?
No.
Okay.
No. So always remember, if you're collecting a sample to do any type of hydraulic properties measurement, and you're not going to run those measurements within a couple days, store it at 4 degrees Celsius.
Yeah, so that didn't happen.
Yeah, because that limits microbial activity. It's going to limit the decay of the roots. That way they stay more intact. Sample storage, people.
and on these things in an extreme, and we've talked about kind of normal cases here, and then we've kind of identified some extreme cases, right?
Yeah.
Where we were talking about, does infiltration and soil health go hand in hand? We said, actually, generally you can see it.
Yeah.
In this case, if we're working in this coarse sand and we've got root growth that's actually forming some of this, some of the soil structure.
Yeah.
Extra special care over that, presumably.
Oh yeah, absolutely. I mean, this makes me think of when we were doing a comparison study with the double ring infiltrometer and the Saturo, and we were inserting it into a little bit more frail soil.
Yeah.
And it takes so much more force to install a double ring infiltrometer because you're dealing with two larger rings. And what we were finding is the force that we had to exert to drive the rings into the ground was actually destroying the structure. Which is an important thing to understand, but I don't want to understand it that way. I'd rather understand that this soil is less stable with maybe looking at aggregate stability or something like that. Because now I don't have an accurate measurement of my hydraulic conductivity because I've destroyed the structure. And it's the same with that type of stuff. Like we need to have the best care to try and maintain the soil in its actual state in the field, which is one of the reasons I like field measurements over lab measurements myself, is we get a better representation of what's actually happening in the field versus when we bring things back to the labs. There's a lot of things that can happen. We don't take care of the sample well. Roots can decay. There's a lot of things that can happen. So those are the things that you have to understand when we're trying to compare, look at impacts of all of these things in the field. And the other part is, the less we have to do to insert the rings, the better. So like most sites use the shorter insertion ring if you can.
For the Seturo?
For the Seturo, for example, because if I'm using a 10 centimeter insertion ring, that's more that I've got to drive it in, and it's more chance I'm going to screw things up when I push it down. So,
well, I'm glad you're bringing this up, because I would say if I had one biggest fault as a researcher, I like to kind of run with it, right? so I like what is there to know about running a HYPROP sample, right, in the field? And so I maybe shouldn't admit it here, but I don't read the manual as much. And I'm just like, let's get to the field and make these measurements, let's go collect the samples and get in. And I think that the poorness of that approach was, apparent on this particular example, but also when you kind of took me through how to run a HYPROP.
Yeah.
A few years ago was my first introduction to it. And I realized that just winging it on some of these things like hydraulic conductivity, infiltration isn't a great way to actually get to the measurements you need.
No,
right?
No. Sometimes there is some care that's needed, and just basic understanding of the things that you're doing and how it impacts the quality of your measurements. Right. I probably have my former advisor, Christine Morgan, to thank for that, because I was more like that until I was under her tutelage. And when I made mistakes, she was like, well, did you read the literature? Did you read the manuals? Did you read the documentation? I'm like, well, no. and so she kind of was like, well, you've got to have better practices here. So
she was also my student worker. So
yeah.
It must have all come back to me. I'm just kidding. I'm sure she probably taught me all of that as a grad student as well. Okay, Brad, we're having too much fun again.
No, that's good, because again, you guys are great at segues. Speaking of correct HYPROP use, we did have a new publication come out that was shared on social media about modifying the HYPROP. Just from, I think this is from the abstract, but basically the quote says, to expedite the method, here we propose a modification of the HYPROP that facilitates consistent temperature and airflow around and over the soil sample ring to ensure constant evaporation from the soil sample. So I just wanted to get your thoughts, maybe a little bit more information on hacking the HYPROP and what you think about this new modification.
Yeah. Is it a hack?
It is not a hack.
Actually, I think I've seen this before.
Yeah, it's actually a really, I had the joy of actually speaking with the author of this paper, Giannis, a couple days ago, and so we talked about this because I saw this post and I was like, oh, that's really cool. I want to kind of learn more about what you're doing and talk about some of my experience. And it was really interesting to hear some of the challenges he had and why they wanted to do some of this stuff. And so they're in Greece, or in one of the islands in Greece, and their lab isn't super well temperature controlled. And so they were seeing diurnal changes in the evaporation rate. And so you could actually see it in their HYPROP measurements. So he's like, yeah, we needed to control the temperature better. And because at first I was like, well, why don't you just use desiccant? Because another way to do this, to speed up the measurement, which this is a common thing that many people want to do, because typically it takes a while. It takes anywhere from 3 to 7, and on some soils
we get back to my
days.
own impatience.
Yes.
Let's move this thing along.
Yeah.
Okay.
But ultimately, the goal is if we can increase the evaporation rate in a way that doesn't violate the assumptions of the measurement. So we want to make sure we stay within the phase 1 evaporation rate. Then let's find a way to do it. And oftentimes when I talk with people about this, I'm like, well, put your HYPROP in a chamber with desiccant, increase that vapor pressure deficit, and that's going to increase your evaporation rate. That's a great approach, but he mentioned, he's like, yeah, but one of our big issues is that our temperature changes so much. And what they actually did is wrapped the HYPROP core itself with a heating element, and they maintained the temperature at a constant temperature around the core. And I was like, oh, that actually makes a lot of sense.
But it's not like it was on fire.
It wasn't on fire.
I mean, they limited the diurnal temperatures. I mean, presumably it was like 25 degrees
Yeah,
something
I think they were doing 30 or 35,
Okay.
which is still fine. You don't want to go too hot.
That's what I'm getting at here, Leo.
Yeah.
I'd probably like, let's do 100.
Right.
Let's get this thing rolling.
Again, we're talking about violating the assumptions of the measurement.
Exactly.
As long as you don't increase the temperature too much, and you know the temperature, the HYPROP's measuring the temperature of the soil anyways,
Yeah.
making correct for all
Okay.
of that. And so maintaining it at a constant temperature is fine. And the other thing they did is they put a little fan in the chamber, and it was just a small computer fan. And at first I was a little worried about it when I saw the experiment, and I was like, oh no, they're using a fan, because the fans are probably one of the worst things we can do.
So I wondered about that. Can you just talk about fans? Because it seems like I've seen fans in use with HYPROPs before.
Yeah.
Well, what's the problem with the fan?
Yeah.
Is it adjusting the weight? I mean,
There's
the scale
two issues with it. There's if you're blowing air right over the scale, it affects the weight measurement and makes it really noisy. Which isn't good.
That's was my concern.
But the other actually more critical factor, both are critical, is because you're increasing that boundary layer conductance so much by having air movement, as you know, Colin, in biophysics,
Sure.
wind speed has a really big impact on the boundary layer conductance. And that increases the evaporation rate to too high of a level where you're actually violating the assumptions in the measurement.
Yeah.
And so yeah, we have to be careful with that. So that's why the desiccant, I think, is just enough. But what he was doing here is just a small computer fan, which was just pulling air out, and it's not moving that much air.
Okay.
It's just enough to pull some of that moisture out of the chamber. And so in a way, it's kind of like the desiccant, where it's just pulling some of the moisture out, and it's not really impacting the measurement. So overall, I actually liked the method, especially the temperature control part. And if you're working in an area where you have poor temperature control in the room, this is a good approach. But also just using a chamber with desiccant too. If your goal is to just increase the evaporation, increase the speed of the measurement, a chamber with desiccant is probably one of the best ways to go.
But what does that look like? I mean, I'm imagining this, the little space, flying saucer shaped thing.
Yeah.
With our desiccant in the bottom, but how do you do the cords? What do you do for all?
Yeah, so you do need to have a way to seal the cords up when it comes out.
So you do run the cords out through your chamber, but
Yeah.
you put the scale and everything inside this.
Yeah, now there's only two cords that happen out, the power cable for the scale and the USB cable that's going to the computer. And I've seen a lot of really nice setups. I mean, if you're get really fancy with it, you can have a USB hub in your chamber that you connect everything to through there, and then that runs to your computer. That might be a little bit too high, but you do want to seal it up just so that way you're really driving that relative humidity down with the dessicant and only pulling moisture out of the HYPROP. But
now again, is this an edge condition? I mean, because I got good. I mean, we run in the lab here without any desiccant and stuff like that. Do I need to do that?
Probably not. It's not as big of a deal here. Our relative humidities in our environment are a little bit lower.
Okay.
But if I'm working in a really high relative humidity environment, I'm going to see a big difference in how fast the samples can dry down.
Yeah.
And if sample throughput is a big challenge, we also don't have to run through hundreds of samples all the time. And people that are trying to run through, 20, 30, 40 samples and get through those measurements, if you can increase that.
I think that's your best point, or not best point, but a great point to make. We do these on ones and twos. I do student projects. We have field sites that we're bringing in. There are some people who are doing a massive amount of sampling.
Yeah.
And this is something that they may think about to really, take a front effort, but eventually help you with throughput.
Yeah, exactly. Yeah.
Okay, Brad, that was fun. What do we got?
All right. So this next one, I'm going to try to rephrase this a little bit, but basically they're asking for best practices to properly prepare the soil surface and to calibrate the infiltrometer to best perform field infiltration measurements.
Oh, great question.
Yeah.
So typically, when I'm going out making measurements, I'm assuming this is referring to surface infiltration measurements. Let's say it's something like the Citro. I'm going to try and remove any large debris from the site, especially if it's in the area that I'm going to insert the ring. So I don't want to see like branches or rocks within that area, because if you're driving right on something big like that, it's going to create a huge gouge when you're pushing it. Other than that, I don't want to touch the surface of the soil. I want to leave it in its
So I got a question for you. Okay? Yeah, you knew I would. So in our lab at Texas A&M, we were studying, macro pore flow with the dye study. Something that we were doing quite a bit back in the late '90s into that ship's clay or whatever. Yeah, Houston black clay. I don't remember what it was, but there were cracks in there. They're visible from the surface. Okay, maybe it's an edge case. We've been dealing with this a little bit, but how do you deal with that? Yeah. So you want to go out there, you want to make these measurements, and you got cracks. Do you close your eyes, and throw a penny into the air and set it on the penny? What do you do?
Those, it's not necessarily an edge case because there's a lot of highly expansive soils like that around the world, but they present a big challenge when it comes to making those measurements because those cracks,
they'll eat up a whole tank of water.
They eat a whole tank of water. And so a good example of this is I was working on a site that I didn't think I was over a crack.
Okay.
And that's one thing I do. If I am working in those shrink swell soils, I will inspect for any large cracks. We can't measure over a large crack. It just takes on so much water. But at this site, I was like, okay, it looks like I'm pretty clear. So installed my rings, set up the measurement. And I was working with some of the folks at the NRCS. We were doing a pit study at the same time. So I was like, okay, well, I'm going to go over here and see what they're doing. I left my stuff running because I set it up to be pretty much fully automated. And I come back and my trailer is empty. Completely 500 gallons of water was gone.
Was there water in their NRCS pit?
And luckily I was far enough away because it probably, if I was close enough, there would have been 500 gallons of water in the pit. But I came back and I was just completely astonished at the fact that I'd gone through 500 gallons of water in maybe an hour and a half. And it turns out I was right over a crack. And the funny thing about cracking soils is if you just get a little bit of surface wetting, the cracks can close at the surface and then still be a huge void down below that. And then once you start infiltrating, the crack just opens back up and the water starts pouring through that crack. So when I was doing work on those shrink swell soils, I actually timed all of my measurements right after the wet season. Okay. That way the risk of cracks was the least.
So we only do Saturo measurements in the spring.
Yeah, in Texas, that's really the only time you can do it.
I think that helps.
Yeah.
So anyway, keep going with site preparation.
Yeah. So other than that, obviously, if you're dealing with tall vegetation that you need to clear from the site, we don't want to have a bunch of grass pushing up into the sensor. So I will come out with some trimmers and clip the grass down to at least 4 or 5 centimeters.
But there's no need to clear the vegetation up.
No. You don't want to because you're going to disturb the structure that's there. So
I'm glad you mentioned that, and sorry to interrupt.
No.
But this is something that if you don't read the manual, you may just assume that you need to just go clear a surface because it would be different with something like the mini disc infiltrometer or a Guelph permeameter,
a borehole permeameter,
something like that. You do something different. So knowing what the site prep looks like really important.
It is, it's really important, and we do see this mistake sometimes where people go out and start clearing stuff out. It's like
just dig a hole, or
I mean, it's great if you want to get down to a deeper layer. And
can you do that?
You can.
So people ask us, hey, we want to not do it at the surface when it's low. So you can do that.
Yeah, you can excavate down to a lower layer. I mean, it's no different than if you were doing a borehole measurement or anything. I mean, you're going to disturb the soil a little bit anyways. So, but what I would do is if I am going to try to get down, I'm going to excavate a little bit, and then I'm going to carefully prep the surface, maybe with a knife, and just kind of picking away at it. That way you're pulling the soil, but not really smearing it. Yeah. Because once you start, especially if it's wet, you start smearing the soil, you're going to start closing off those pores.
Yeah, that seems like a big concern. I mean, I've seen that done in the field where I've come up and they're like, right. And I'm like, how's the water going to get in there?
Yeah.
You just made a butter paste.
Exactly. Yeah. And that's why, like when we did pit studies, for example, like, and we're trying to prep the surface of the pit to view, we would pick at it with a knife. We wouldn't just smear the soil. Yeah. We're trying to just pull the soil off and maintain some of those pores. And it's the same thing if I'm trying to do an excavation to do a measure down lower. Now, if you're trying to measure really deep, it practically just becomes impossible. But if I'm just trying to get down to maybe 10, 15, 20 centimeters and just measure a little bit deeper, that's totally fine. Just make sure you prep your surface.
Yep.
Right.
No, I think that.
Yeah.
And I interrupted. You were talking about clipping the grass.
Yeah.
Anything else that I'm missing?
No, I think it's mostly just trimming the vegetation. Make sure you get that down. Other than that, just make sure nothing is within your ring area that you're going to push down. And then actually, once you get the ring inserted into the ground, obviously make sure when you're inserting the ring, it's a stable insertion. You're not going in a wobbly pattern.
Yep.
You want a nice straight down insertion. And then I often recommend coming in with a pencil eraser edge and just tamping the soil around the edge of the ring. So just going around the edge of the ring and tamping the soil just to kind of seal up and reduce the risk of preferential flow just down the ring edge.
Down and down and up or whatever.
Yeah, exactly. Yeah.
So, I mean, these are the things that you don't think about.
Yeah.
I'm glad we have Leo around to correct all my poor experimental.
Well, and it's because I've made the same mistakes in the past. So I'm learning from all of my mistakes.
I guess that's why we do office hours, right?
Exactly.
Okay. Brad, did we nail that one? I think we got it.
I think we're good. So we've got 5 to 10 minutes left.
Okay.
So we'll see. The way things are going, this might be our last question, but we'll see.
I suddenly realized
I
realized we just almost ate up a whole hour having fun here.
Yeah.
So sorry, guys.
It's all right. It's good. Okay. So this one, and I don't want to turn this into a bash session, but this does get to broader, maybe some broader issues within scientific measurement and other things like that. But the question is basically, why is the double ring method still commonplace if there are now newer methods like the dual head?
Yeah. No, that's a really good question. And some of it is just, it takes time for people to trust new methods.
I think one retirement at a time, right?
Yeah, exactly. Yeah. It takes time for people to trust new methods. They want to see the literature out there. The beautiful thing about the dual head and the Saturo is the literature has been out there for 30 plus years. So the methodology that it's based on is been sound science for years. There just hasn't been easy to use tools to make this approach.
But I think, I mean, that's absolutely true. But when you dig a little deeper, I think when you and I were talking about this, you always say, well, think about the alpha value. Like, it's not just that the dual head and the dual ring are the exact same measurement and we put it in a box and that's not in a box. There are things that make the dual head more accurate and more robust to different soil types, right?
There are, yeah. And the alpha value that Colin's referring to are the macroscopic capillary length factor.
See, that's way easier to say as alpha value.
Which is related, essentially it's just related to the sorptivity of the soil. It's a factor that we use to correct from a ring infiltrometer. Because we know that water doesn't just move vertically, it moves horizontally, and we want to correct that value to get that vertical flow value. With tools like the double ring, we traditionally have just estimated what that alpha value was. And that leaves a lot of room for error because you're essentially having to make judgments on the soil type, but also, like, is it a well-structured soil? Is it a poorly structured soil? What are some of these other things that can impact it? The beautiful thing about the dual head approach is it actually allows us to directly characterize that.
Why?
Because when we're infiltrating water at two different pressure heads, we can look at the rate of change between those two different pressure heads and use that to and mathematically determine what the sorptivity is and what the that alpha value is.
So is it a case of, maybe this is oversimplified, but two equations, two unknowns, essentially, because we've got two different infiltration heads, and we can solve the equations if we doing two different things.
Exactly. That's exactly what we're doing. And there's a great theory section right up in the manual on this that I highly recommend reading, and it directs you to a couple papers that we have used to base the methodology off of. One is from the Methods of Soil Analysis, and the other is from John Nemo. Where we kind of took the best of both worlds that we liked and kind of combined that together. And some of the stuff that Galen did there was really amazing, along with the work that John Norman was doing there. But to go back to why the double ring is still commonplace is because people have double rings sitting around. And also in the engineering world, which is really the more tricky one, in the science world, once we start publishing and people start trusting the literature, it's pretty easy to start adopting new methods. On the engineering side of things, standards are
they save lives.
They do.
You know, they're there for a reason. But will there be a standard for something like this?
Yeah, and there is, and it's been in the works for quite some time. And the challenge with standards is it just takes a long time to get those standards through. And engineers have to rely on methods that are based on standards because it protects them from liability standpoint. It's like, no, this was based on ASTM standard XYZ. And so that helps protect them. In the science side of things, we don't really have to worry about that as much. But, you know, it just takes more time to replace those methods. That's why some of the tools like pressure plates and filter paper method still are being used.
We're talking for water potential.
For water potential. But it's the same challenge. It just takes time. And also maybe goes back to what Colin said, one retirement at a time.
Yeah. but honestly, I mean, I fall into this trap like everybody. I know the way I like to do things, and that's probably why I make errors sometimes on the HYPROP. I have a methodology that's in my head. I go follow the methodology, you know, and it's not necessarily the best way to get the number.
Yeah.
Right?
Yeah.
Do we got time for one more?
Let's see. We could do a quick, I don't want to say lightning round, but
okay, wow.
Okay, how about can you do a 1 minute answer on this one? Okay. So they're basically asking how many measurements do you expect to make in a field to account for variability, and how do you navigate that issue?
Yes, one of my favorite questions. A couple things that you want to look at. How does their soil type change across that field? So maybe use a soil map, go hop onto Web Soil Survey, or do an EM map of the field and look at the variability. That's what I did for my research to identify those zones of variability, and then start measuring in those different zones. The other area is hill slope position. Do we have big changes in elevation? And what is our katina effect there? As we know, soil hill slope positions impact how soils form.
What is the katina?
The katina effect is when you're looking at you've got your hill slopes, you have your summit, you have your shoulder, you've got your the actual sloping part, you have the foot slope, and the nutrients collect down at the lower portion. So that actually impacts the hydraulic properties.
Just wanted to make sure we were, you know, okay, I'm not, what the heck is a katina?
Yeah.
It's something we talk about in Soil 201, but
yeah, it is a good thing to clarify. So look at those things and try and measure across those different areas. Soil type and landscape position are the biggest factors that I think make a difference.
I should have timed that. Oh yeah.
Did I do that in a minute?
Yeah.
Close enough. We'll call it good. All right. I think that's it. We are up at the hour here. So that's going to wrap it up for us today. Again, thank you to everybody who's joined us. We hope that you enjoyed this discussion. Thank you again for all the great questions. There are several questions that we didn't get to. If we did not get to your question live, we do have folks on our environment team who will be able to get back to you via email to answer your question directly. Also, please consider answering the short survey that will appear after we finish here, just to let us know what types of Q&A themes you'd like to see in the future. And for more information on what you've heard today, please visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future Meter Office Hours events. Thanks again, stay safe, and have a great day.